Alright, in this video we start with problem 8 off test 4 of the fall 2013 AP Physics course. Car uniformly accelerates from 23 meters per second to 41 meters per second in 13 seconds. Alright, what's acceleration? A is equal to delta V over delta T. We don't have to be concerned about any differences between instantaneous acceleration and average acceleration because the acceleration is constant. So average is the same thing as instantaneous. It says it goes to 41 meters per second minus its initial was 23 meters per second and did this over 13 seconds. So 1.38 meters per second squared. How far did the car travel? Well, it's constant acceleration. That means that we can apply the kinematic equations. So applying the kinematic equations for this problem, there's a couple of different ways you could do it. Doesn't matter which one of the two, but one of the ways to do it is to go Vx squared is equal to Vx naught squared plus 2ax times x minus x naught. So we have 2ax x minus x naught is equal to Vx squared minus the initial velocity squared x minus x naught, which is what I'm asked for, is equal to Vx squared minus Vx naught squared, all of that over 2 times acceleration. We have everything that we need to answer the problem from the numbers we've already obtained. So x minus x naught is equal to 41 meters per second. Square that. Subtract 23 meters per second and divide by 2 times acceleration, 1.38 meters per second squared. And if you do that, you get approximately 417 meters. So that's how far it went before it did that. There are other ways to work the problem. For instance, you could have also found, as an alternative, you could have found that delta x was equal to Vx plus Vx naught. Let me pull this up a little bit. Times Vx minus Vx naught, all of this over 2 times Vx minus Vx naught, and that times delta t. Now what have I done here? Well, this is just a Vx minus Vx naught over delta t. That's a sub x, and this thing here could have been factored into Vx plus Vx naught times Vx minus Vx naught. That's just the perfect square differences. And then if you do that, you would have found that it's Vx plus Vx naught over 2 delta t. Well, what this is this is V average. So you also could have factored that a little bit more and found that it's V average times delta t. And if you plug that in, you get the same answer. But this was plenty good enough because you had all the numbers and you weren't trying to prove some sort of formula. So that's the way I expect most of you would have solved it. Problem number 9 on the exam. So in problem number 9, it's a relatively quick problem. We have a ball, and I've chosen to make my ball here at y naught equals 0 meters. And I've chosen for this problem to declare this to be the plus y direction. So the ball falls and eventually it hits the water at some height y, which I don't know. Other things I know, let's fill out my table. Y naught is 0 meters. Y I don't know. Vy naught, it says it's dropped. That means it starts from rest. Vy, I don't know. Ay, in this case, because I've pointed my axis down, the acceleration is a positive g. Again, you don't have to do that. You just have to be consistent. And t, I don't know t. Or did I know t? Yes, I do know t. I take that back. I was about to say, got to know something else. 10 seconds. There can never be more than two unknowns when setting up a one-dimensional kinematic equation problem. So I knew I must have missed something in doing it. It said the ball hits the water 10 seconds later. Y is equal to y naught plus Vy naught t plus 1/2 gt squared. And Vy naught was 0. Y naught was 0. So y is 1/2 times 9.8 meters per second squared times 10 seconds squared. Put that in and you find that it's 490 meters approximately. Okay, and that's the end of problem number 9. Problem number 10. A plane lands on a runway traveling at 210 meters per second. All right. Going at Vx naught, 210 meters per second. I will consider this location to be x naught equals 0 meters. And some later time, I have the plane over here now. And this x, it says, it's going to stop in 460 meters. Okay. And stop means that Vx will be 0 meters per second. And it asks for what is the smallest deceleration possible. So I'm looking for a sub x. Let me go ahead and fill out my table. 0 meters. X is 460 meters. Vx naught is 210 meters per second. Vx is 0 meters per second. Ax is unknown. T is unknown. Only two things I don't know. Easiest way to work it, the range equation, Vx squared is equal to Vx naught squared plus 2 times the acceleration in x times x minus x naught, the displacement. Vx is 0. Rearranging that equation, I get 2ax is equal to minus Vx naught squared over x minus x naught. And x naught happened to be 0 as well. So ax is minus Vx naught squared over 2 times the final location. The minus indicates that the acceleration is in the negative x direction while the velocity is in the positive x, so the object was in fact slowing down. It was decelerating as we were told. Put my numbers in this. Minus 210 meters per second. I'm going to square that. And I'm going to divide that by 2 times 460 meters. Put that in together. I get minus 47.9 meters per second squared. And that's the answer to that problem. And that was all of the regular test questions. On the next video, we'll talk a little bit about the bonus questions, which weren't too complicated. In fact, I guess maybe we have time to do those here. In the bonus questions, it says that you're performing an experiment and you've got a position time graph that looks like this, and it starts at 2.45 and it has a slope of minus 1.65. This is a constant velocity problem. The acceleration of the object is 0 because it's constant velocity. The velocity I can get by looking at the coefficient, which is a. So v is minus 1.65 meters per second. The object's displacement is a little bit more challenging in the sense that I have to read it from the graph. I have to find the change in the position on the graph. So delta x equal x2 minus x naught. Delta x can be found a couple of different ways. You can read a directly graph, or you can just use the fact that's 1.65 meters per second, and it's doing this for 2 seconds, so the displacement was minus 3.30 meters. And the last set of questions on there, again, all of that I should say was from the previous test. I'm just checking to make sure you mastered test 3. And the last 2 things was kinematics. An object with no size and fixed mass is called a particle. And kinematics is the study of motion. And this covers all the problems on test number